Alright, so in this video, I'm gonna be explaining another important article. The title is Complementary Domain Adaptation and Generalization for Unsupervised Continual Domain Shift Learning. So when we see continual, it means that there should be a sequence of tasks. So we don't want to forget the previous things that we have learned. And so this paper in 2023, continual domain shift poses a significant challenge in real-world applications, particularly in situations where labeled data is not available for new domains. The challenge of accurate knowledge in this problem setting is referred to as unsupervised continual domain shift learning. Existing methods for domain adaptation and generalization have limitations in addressing this issue, as they focus either on adapting to a specific domain or generalizing to unseen domain, but not both. So they propose complementary domain adaptation and generalization, which is a simple yet effective learning framework that combines domain adaptation and generalization. In generalization, we have an unseen target, but in domain adaptation, we have a fixed target. So that is the only difference between them. So they combine it in a complementary manner to achieve three major goals of unsupervised continual domain shift learning: adapting to a current domain, generalizing to unseen domains, and preventing forgetting of previously seen domains. For example, in continual learning, we are talking about catastrophic forgetting. And we, for example, design regularizers such that the difference between the weights at different stages are very small. So the difference is small. So we define this loss. And so our approach is model agnostic, meaning that it is compatible with any existing domain adaptation and generalization. We evaluated it on several data sets. Okay, so our proposed complementary domain adaptation and generalization framework for unsupervised domain shift learning. You see that you have continual domain shift with unlabeled data. It means that at any instance of time, or let's say at any episode, we have a different target domain. So at time t-1, we have this target. Another time we have sketches. Another time we have real images. And so it's a continual domain shift. So what they do is very interesting. They initialize their domain adaptation from what they have learned from domain generalization. So it improves adaptation. And what they have learned from domain adaptation is that they use the pseudo-label generation to improve the generalization. So this is an implementation that they have a source domain, they copy and distill to the domain generalization. They have domain adaptation to get the pseudo-label to use it for domain generalization. Because it's a loop, you could also use the pseudo-label for domain generalization. And this continues because at different time they have different target domains, and we have this replay buffer as well. You know, these concept, experience, replay buffer, catastrophic forgetting, all of these I've explained in the playlist for continual learning. So the first domain is regarded as source domain that is used to initially learn the target task. Different from other domains, it consists of labeled samples. After a model is initially trained with source domains, it sequentially encounters a series of target domains. In contrast to the source domains, the target domains do not provide any label information to the model. As we assume that the model encounters them after the deployment, moreover, we consider more realistic setting that samples from previously experienced domains are not fully accessible, but are partially available via a replay buffer with a limited capacity. Therefore, the model has to properly improve its generalization ability in an unsupervised manner by mainly using unlabeled samples from target domain at each stage of time. So they aim to prevent catastrophic forgetting from previously seen domains. So there are three main goals. First, they seek to achieve domain adaptation. Second, they achieve domain generalization. And finally, as I said, they prevent catastrophic forgetting of knowledge gained from previously seen domains. So there is a trade-off between domain adaptation and domain generalization. To resolve this trade-off, they propose a novel framework called complementary domain adaptation and generalization, which is highly effective yet remarkably simple. Unlike other approaches that require complicated architectures or learning methods, our model, our framework relies on a straightforward and intuitive idea. The intuition is that maintaining two separate models for domain adaptation and domain generalization by having two distinct models optimized for their respective goals, the framework eliminates the need for complicated techniques that attempt to balance domain adaptation and domain generalization within a single model. So to initially learn a given target, we train domain generalization model from scratch with a set of labeled samples from source domain. This stage can be approached by a single source domain generalization method. In that way, we simply minimize the following cross-entropy loss over the source domain data with enhanced data augmentation. So in general, unsupervised source-free domain adaptation approaches involve initially training a source model with the source domain data and further updating the source model with unlabeled data from a new target domain. However, in our proposed framework, the domain adaptation model utilizes the parameters of the previous domain generalization model for its initialization. So to apply an approach for the current target domain, DT, we first initialize the domain adaptation model with parameters of the domain generalization model trained from previously experienced domains, treating it as a source model. Then we freeze the classifier head and only update the feature extractor part using. So this freezing is very interesting. You see it in different frameworks. For example, in model editing, you freeze a model, then you add it with another model, the edit, but the total model is called the edited model. And then we make sure that the KL divergence between what your original model, this is original model, has predicted, and the total model, this one, the KL divergence between their prediction, between the softmax of their prediction, is small. So we put it in a loss and we train it. So then we can add different patches, so we can grow our model. It's very natural approach. So freezing, even in transfer learning, we freeze and then train on other layers. So it's very important in deep learning. So we simply use empirical risk minimization along with an enhanced data augmentation method for training the domain generalization. So for each unlabeled sample, we compute its pseudo label y hat. And theta star here is obtained by minimizing the LDA, loss of domain adaptation at time t. And this delta k here is just the case element of the softmax output. Now, by using the resulting pseudo-labels as training labels for the domain generalization, we construct a pseudo-label dataset. We then update the domain generalization model, and we have the following loss. This loss where theta is just initialized with the optimal parameters of domain generalization in previous domains. This is our previous domain. So forgetting alleviation is crucial in unsupervised continual learning, shift learning, and where limited access to data from previous domains makes it challenging to maintain performance on previous tasks. When encountering a new target domain, the performance of the domain generalization model on previous domains tends to degrade, which is commonly referred to as catastrophic forgetting in continual learning. So to address this issue, we add a simple distillation loss to the loss of the domain generalization to ensure that the model retains the knowledge gained from previous domains while learning from the current target domain. And this is the KL divergence between these two. And for the final loss to update the domain generalization model is just the addition of distillation and the original loss. Target domain adaptation for each domain is performance measured on the domain right after its training stage. The target domain adaptation of the tth domain is just test accuracy on the domain D sub t with model F. So these are target domain adaptation. We have T number of domains. So what about evaluation for forgetting alleviation? For each domain is evaluated by the average performance on the domain after the model has been trained on subsequent domains. This forgetting alleviation of the tth domain can be written like this. So they propose a learning framework that combines domain adaptation and domain generalization. And their approach is model agnostic. It could be used for any domain adaptation and generalization algorithm